guys. Today's topic is magnetism and magnetic field. So, we'll first of all be looking at the meaning of a magnet and some other things. Alright. In physics, magnetism is a force that can attract. Definitely, when we're talking about all these type of forces, we have magnetic force, electric force, electromagnetic force, and types of, and like that. So magnetism in physics is a force that can attract. When you say something is attracting, is pulling closer, or repel. When something is repelling, is pushing away. You understand? We can have let me use an example. Let's say we have Tamilore and Tumishe. So when we say attract, that is two of them, they are coming together. When we say repel, that is Tamilore does not even want to have anything to do with Tumishe. So he's always making sure the distance between two of them is very far. So that's what we're talking about when we talk about repelling and attracting. So that's magnetism. It is a force. Magnetism is not the ability, it's a force that can attract. It's a force that can attract. So I don't want to ask somebody when we resume and somebody will tell me magnetism is an ability. No, it is not an ability, it's a force. Alright, the power of attraction between two, and that's another definition actually. All these that I are seeing here, they are just different definitions actually. Another definition is saying, normally English definition, is the power of attraction between two elements. The power of attraction between two elements. Alright, so it can also be the power of repulsion between two elements. Do you get? So don't get confused because they use the power of attraction there. In simpler words, it is another definition. In simpler words, it is a property of certain substances which pull closer or repel other objects. We said that magnetic materials are matter that is attracted by magnets. Anything that gets attracted to a magnet. Are you following? Anything that gets attracted to a magnet, they are called magnetic materials. So all those iron, actually, definitely, magnets get attracted to metals. Wherever you find a metal, you can always put a magnet there because it definitely to attract. So that metal is called a magnetic material. So whatever gets attracted to a magnet, whatever comes closer to a magnet or is attracted to a magnet, they are called magnetic material. And that thing is that it says it attracts opposite poles and repel same poles. Just like the example I cited earlier. When we have a male and a male and we have a male and a female and a male will always repel each other. We are talking in terms of magnet now. A male and a male will always repel each other. So what we're talking about in that respect is that anything that has the same poles, they will what? They will repel. Once you have the same pole, they will repel. Once you have opposite poles, they will. So this pole, let's come down to our level by using this pole as human beings. So that's why you will see that a guy and a guy actually. Let's say, I used to tell you guys most of the time, whenever a new student comes to the class and the new student is a guy, you will notice that most of the guys in the class, they might not be really happy like that to an extent. Do you get? It's not that they might not be happy, but they might just feel that okay, he's a guy and nothing more. Do you get? So there's this repulsion. Do you get? Compared to the way the ladies will smile. I'm talking about when let's say I'm talking about for higher students actually. Compared to the way a lady will smile. Whereby if a guy should come to the class very first time, you see that some ladies will just be smiling, just blushing for it. They don't have any reason to blush, but they just find themselves blushing actually. So it shows that there's this kind of attraction, and naturally we've been created that when we see the opposite kind of person, we will definitely get attracted, even in biology. So I'm just using that example to cite this. So if we have a north pole and a north pole, it will always repel. If we have a south pole and a north pole, it will attract. So that's what I'm trying to say in essence here. So I think moving on to the next slide. I think we are done with magnetism like that. So moving on to the next slide. Okay, saying magnetic and non-magnetic materials. magnetic and non-magnetic materials. What are magnetic materials? And like I have said earlier, magnetic materials are material that is attracted by magnet. Okay, any material that gets attracted to a magnet, they are called magnetic materials. And examples, we have the iron, steel, nickel, cobalt, and many alloys based on these metals actually. So all these things actually are all magnetic materials. But non-magnetic materials are materials that are not always attracted to magnets. So just like you have a book now, a magnet cannot be attracted to a paper. Are you following? A magnet cannot be attracted to a wood. A magnet cannot be attracted to a plastic. So those are non-magnetic materials. So in that respect, we keep on moving. Let's move to the next slide, to the next page. Types of magnetism, or sorry, type of magnetism or type of magnet. The first type of magnet that we have is called a permanent magnet. A what? A permanent magnet. It's different from this one that we looked at too. This one's, they are just trying to classify magnetic materials. This one is magnetic materials, but this one now is type. So in case I ask you, magnetic materials are different from magnet. Types of magnet: we have permanent magnet and we have the temporary magnet. So the permanent magnets are those. Okay, the permanent magnets are those we are most familiar with, such as the magnet hanging onto our refrigerator door. Okay, yes, you notice our refrigerator now. You notice when you want to close your fridge, you notice that there's something that attracts that fridge glued, that will make it glued to the body of the fridge. You know, when you open it, you know, when you close it, you see that the closing is actually firm. It's not as if it will open again because there's a magnet there. So so what they use there is actually a permanent magnet. They are permanent in sense that once they are magnetized, they retain a level of magnetism. So that's why so anything that retains a high level of magnetism, like when you put two things together and they find it difficult to repel each other, that magnet is called a permanent magnet. So permanent magnets are magnets that they tend to have high level of magnetism. They retain their high level of magnetism once they are magnetized. They don't lose their magnetism or magnetic property easily. So temporary magnets are those which act like permanent. They act. This one, they act. ACT, they act like they will act. They are not real. They act like a permanent magnet when they are within a strong magnetic field. This one now, if they are not within a strong magnetic field, that means they are not a permanent magnet. But once they are within a strong magnetic field, they act like a permanent magnet, but they lose their magnetism when the magnetic field disappears. Are you following? So all this one, they tend to have their magnetic property or when there's a strong magnetic field. So when there's a strong magnetic field, I'm still coming to magnetic field actually. You know, I've told you guys, wherever you have a field is always a region of space under the influence of something. Just like electric field now is a region or space under the influence of what? Electricity. What about a magnet now? A magnet too. So when we say magnetic field, a magnetic field is a region of space under the influence of a what? Of a magnet. So when we say a football field is a region of space. You notice that it is always placed within a particular space. So a football field is a region or space under the influence of what? Footballers, or under the influence of footballers and the ball that they use. So once the ball and the players are present in that field, immediately that field turns to a what? A football field. Once a magnet is present in a field, immediately that field turns to a what? A magnetic field. Once electricity is present in a field, immediately that field turns to a what? It turns to an electric field. Sorry. So temporary magnets, they tend to what? They tend to act. Do you get? So they tend to act whenever they have a strong magnetic field around. So whenever there's no strong magnetic field around, their magnetism tends to what? Disappear. So the difference is that for permanence, they retain their magnetic property. Whether you have a strong magnetic field or you don't have a strong magnetic field, they retain it. But for temporary magnets, they don't actually. Once the magnetic field is off, or once the magnetic field disappears, they lose their magnetism or their magnetic properties. Examples would be paper clips and nails and other soft irons. Examples would be paper clips and nails and other soft irons. So those are the examples that we have. So moving on to the next one. General properties of a magnet. All magnets have two types of poles. I've told you earlier, we have the north seeking poles, or we call it the north poles, or with south seeking poles, we call it the south pole. So the magnetic strength is strongest at the pole. So when you have a magnet, you only find the magnetic strength always at the pole. The magnetic strength is always at the poles. You know, a magnet used to have body. You know, when we have a bar magnet now, it has both it has two edges, sorry, and it has a flat body. That flat body now, the magnetic strength is not strong there. How I wish. Okay, let me see if I can actually move to a bar magnet. If I have a bar magnet, okay, see a bar magnet. Can you see this bar magnet? Can you see that this point is the north pole, this point is the south pole? So okay, ask yourself now, from here to here, now from here to here, what is happening from there? From here to here, I'm coming, sorry, I want to show you something. Okay, now if this place is the north pole and this place is the what, is the south pole, so from here to here is just what, is just the body. Are you following? From there to there is just the body. But one thing I want to explain to you is that the strength of the magnet is always at the north and south pole. All this place like this, you can't find the strength of the magnet here around this place. That's why you notice, if you want to put pin, if you want to put a pin, if you want a pin to get attracted to a magnet, you see that even if you put the pin here, the pin will just find a way of coming to the what, to the edge of the magnet. Are you following? Just try it at home. Try to put a pin around the flat surface, but you see that the pin will just tend to move towards the what, either the north pole or the south pole, because the strength of a magnet is always at these what, two poles. Are you following? The strength of the magnet is always at these two poles. So let's go back to where we are coming from. Let's go back to where we are coming from. So I just used that one to explain something. I'm coming. Okay, so I'm sorry, I'm coming, please. So moving back to the general property. So I've explained the strength, where you always find the strength is always at the pole. So when you freely suspend a bar magnet in a horizontal position, exactly, when you freely suspend the bar magnet in a horizontal position, so when we're talking about horizontal positions, this is what we're talking about now. Look, sorry, this is not what I want to do. Coming, sorry, no. Okay, can you see now? I've actually drawn a bar magnet here. Let's assume this is a bar magnet, or is in an horizontal position. So it says the magnetic field of the bar magnet will interact with the magnetic field of the earth. The magnetic field, that is the magnetic field of this bar magnet, will interact with the magnetic field of the earth. This will cause the bar magnet to come to rest in a north-south direction, where the north pole of the magnet points to the north pole of the earth. You get what? So what this thing is trying to say is that this bar magnet now, the way it's horizontal like this, what it's trying to tell us is that the north pole of this magnet will point to the north pole of the earth when it is freely, when you freely suspend a bar magnet in a horizontal position. That is when it is freely suspended in a horizontal position. The magnetic field, not the magnet now, the magnetic field, are you following, which we cannot see. Do you get? We can't see a field actually. They are imaginary lines. Are you following? Which the magnetic field of the bar magnet will interact with the magnetic field of the earth. You know, both of them we can't see it. They are magnetic field. They are imaginary lines. So they are not saying the magnet will interact with the earth. Oh, are you following? Don't get the point. Magnetic field of the bar magnet, magnetic field of the earth. So it will interact. So if they ask you what will happen when you suspend a bar magnet in a horizontal position, number one thing that will happen is that the magnetic field of the bar magnet will interact with the magnetic field of the earth. And that one is that, what will that happen after that one? It will cause the bar magnet to come to rest in a north-south direction. It will cause the bar magnet to come to rest in the north. That's the effect of the interaction of the two magnetic fields, where the north pole of the magnet points to the north pole of the earth. So let's say this is the north and south pole now. This north pole will point to the to the north pole of the earth. And let's say this is the south pole. This south pole, I'm coming. So what I'm trying to say is that the north pole actually will come to the end of the class. And so assignment on drives, number one is define drive mechanism. You should be able to do this. Define drive mechanism, sorry. Number 2, list 3 types of drive mechanism, which I said. Number 3 is define driving and driven pulley. And number 4, mention 4 types of belt. And the last one, mention 5 applications. No, not applications actually. Mention 3 advantages of a belt drive, a belt and pulley drive. So that's it for mention 3. Okay, number 1, define drive mechanism. Number 2, list 3 types of drive mechanism. Number 3, define driving and driven pulley. Number 4, mention 4 types of belt. Number 5, mention 3 advantages of a belt and a pulley drive. So now we have come to the end of the class. Have a wonderful time. And please submit the assignment this week, please. Thank you very much. Trying to say is that the north pole of the magnet points to the north pole of the earth. You know, the earth so has the north pole and the south pole. So why the south pole of the magnet will point to the south pole of the earth? So that's what this one is just a simple thing. So if you are asked in the exam, when you freely suspend a magnet in the horizontal position, what are the things that will happen? The first one that will happen is that the magnetic field, nobody should tell me the magnet of a bar magnet. Magnetic field of a bar magnet will interact with the magnetic field of the earth, number 1, and it will cause the magnet to come to rest in a north-south direction, number 2. Number 3 is that what? The north pole of the magnet points to the north pole of the earth. That is all about that. I'm very sure you actually got what I said there. So let me just continue. So we move to properties of magnets. Properties of a magnet. Number 1, properties that like poles repel, unlike poles attract. I've told you, when we talk about like poles, when we are talking about like poles, they are talking about same poles. And when they are talking about unlike poles, they are talking about different poles. And I've told you already, north and north will repel, south and north, or north and south will attract. Then another one says magnets attract magnetic materials such as iron. We have said it, and these materials are called what? They are called what? What are they called? They are called magnetic materials. And the ones that don't get attracted, they are called non-magnetic materials, which I have said earlier. So the stronger a magnet, the larger the attractive or repulsive force between other magnets. So if a magnet is very strong, the rate at which it will attract, that is the rate of attraction will be very high. Actually, the rate of attraction will be very large. It will be very large. So the closer together the two magnets are, the greater is the magnetic force between them. So that these are just the normal properties. Like the general properties that they always ask is that like poles and unlike poles. This one, like poles repel, unlike poles attract. And magnet attract magnetic materials. And another one is that the stronger the magnet, the larger the repulsive force or attractive force. And another one, the closer the two magnets are, the greater the magnetic force. The strong, just like when you want to go and fight a war now, and a particular country cannot fight the war alone. If the country should call on a neighboring country to fight the war, just like the one that is happening now with the Boko Haram, if the country should call on another country to help, you will notice that the greater the force will now be greater. So that's what they are trying to say, that if you add two magnets together, that the magnetic force will be greater. Are you following? So if two countries to come together to fight an enemy, you see that the force will be stronger compared to just only one country fighting or facing the enemy. So that's what that is trying to talk about. And that one is called magnetic flux and magnetic field. I've talked about magnetic field already. I said it's a region or space under the influence of a magnet. But this one is saying it's a region around the magnetic material or a moving electric charge within which the force of magnetism acts is called anywhere it is acting, whether it is under the influence or anywhere a magnet acts, is what we call a magnetic field. So it's either this thing must always be there. Anywhere you see field, you must always put a region or space. Don't write a magnetic field is something that a magnet it's not something, and it's not the ability. It is a region or space, because the field is there, so it must always be a region or space under the influence of a magnet. Or you can write a region around a magnetic material or a moving electric charge within which the force of magnetism acts. You can actually say this. But now I'm coming, my point of this thing is magnetic flux. A magnetic flux is a measure of the quantity of magnetism. It is a measure. This one is not the ability, it's not a phenomenon, it's not something, it is a measure. You must always, all these very key points, I want you to take note of it. It is a measure of the quantity of magnetism, being the total number of magnetic lines or force passing through specified area in a magnetic field. So it is a measure of the quantity of magnetism being the total number, or you can say the quantity is a measure of the number of magnetic lines or force passing through a specified area in a magnetic field. So you can just put it like that. It's a measure of the quantity, because what they are trying to say, quantity of magnetism too, is just right. They're just trying to tell you, as you can see, there's a comma, being they're telling you that the quantity of magnetism is also the total number of what magnetic lines. Are you following? So you can just say it's a measure of the total number of magnetic lines of force. So you can just say it is a measure of the total number of magnetic lines of force passing through a specified area. That means when we're talking about a specified area, I want to bring in something now. Let me just explain. I'm coming. So are you getting it? Let's say this is our specified area. So the total number of magnetic lines, that is the total number of magnetic lines. Let me draw a magnetic line. I'm coming. Okay, so the total number of magnetic lines in this area is called a magnetic flux. So that's what they are trying to say, is a measure of the what is a measure, just come from here, is a measure of what the total number of what magnetic lines of force. So these lines are called magnetic lines of force. Are you following? Passing through a specified area. You can see I had to put a box here so that we'll use this as our specified area in a magnetic field. So I'm coming on. There's something I really want to really say again. Alright, can you see something that I just did now? Because I read it now and I just noticed. Is a measure, okay, let's say now, is a measure of the quantity of what? The total number of what? Magnetic lines. That is the total number of these lines. Are you following? The total number of magnetic line of force passing through a specified area. See the specified area, this small box is the specified area. That is what they are trying to tell you, that this specified area again too is in a magnetic field. That means this big box now is what? The magnetic field. So that means the specified area, that is when you have something very big inside that thing that is very big, a portion, you are now taking a portion called a specified area. So the total number of lines, not the total number of lines passing through the whole magnetic field, no, but the total number of what magnetic lines of force passing through the specified area, that is this small box. That again, the specified area is also in the what magnetic field, this big box. Are you following? So that's magnetic flux, is a measure of the total number of magnetic lines of force passing through a specified area in a magnetic field. As you can see here, these are what we call magnetic lines of force. I'm still going to define it. They are imaginary lines. You can't see them. You can't see them. You know, when your magnet and any magnetic materials want to attract, you don't see that thing that is pulling them to attract, but there's something pulling them to attract. Actually, they are called magnetic lines of force. You can see the magnetic lines of force. You can see all these ones that are trying to go out, they are showing repulsion and every other thing. See this one too. This is what that other thing was talking about, that the magnet will shift to the north of the earth. Are you following? That when the magnet is in horizontal, you see now that the magnet has actually shifted. You know this, you know, when we have our globe, you know, this is the north, this is our south. You know this is the north and south. You see that from that last one that I was talking about, this one that I was talking about, let me go back a little. This one that I was talking about, that before we got here, this one that I was talking about, I was saying the north pole of the magnet points to the north pole of the earth. So that's what is happening here actually in this diagram. You see, the north pole has actually shifted, pointing to the north of the earth, and the south pole pointing to the south of the earth. So that's what will happen when you when you freely suspend a bar magnet in an horizontal path. It will happen like this. So that's it. So we move on. Magnetic field. I've spoken about magnetic field, a space or region around the magnet, blah blah blah. And magnetic field is always denoted as B, capital letter B. So whenever you see capital letter B in physics, it's called magnetic field. That's one thing I want you to know. This is another material, so that's why we are seeing this again. So another thing is that now I want to check this on how to locate the magnetic field of a bar magnet. To locate the magnetic field of a bar magnet, we use iron filings. What are we talking about when we say iron filings? When you go to all these weather, you will notice they've already cut iron to an extent that you just see some small pieces of iron on the floor. You will see them. All those small pieces of iron are called iron filings. So whenever we want to know the magnetic field of a bar magnet, and we want to locate the magnetic field of a bar magnet, we use iron filings or magnetic compass. But let's talk about iron filings. When a magnetic compass is far away from a magnet, when a magnetic compass is far away from a magnet, it is not deflected because it is far away. However, when a magnetic compass is closer to the magnet, it is deflected. So that magnetic compass, it has a deflector, just like the one in our ammeter, that thing that used to move, just like the hand of your clock. That's what we call a deflector. So the space or region around the magnet within which a magnetic compass is deflected is known as what? A magnetic field of the bar magnet in the field. So I will show you a picture soon now using iron filings for us to know the magnetic field of the. Can you see? Using iron filings, all these things are called iron filings. Though in Nigeria our own iron filings is not as fresh as this and fine as this. Although this is not even but it's like iron filings. Let's just use it as iron filings actually. So you will notice that they all came to one particular point. Why did they not come to the whole body like this? Now that's why I was telling you that the strength of a magnet is always found at the poles. So they did not come to the whole body. You will just have to pick a point. So all these points actually is where we can call our magnetic field, and they are called, these 2 points already, they are called the poles. So we don't know the one that is the north pole and the south pole, but these 2 points are called the poles. So that's that about iron filings. They tend to move towards the poles of a magnet. So from there we move. We're almost done. I think this 11. Okay, page 11. So now magnetic field, I've talked about it. Magnetic field is represented by a series of lines or paths. After I told you, magnetic field is represented, they are lines, so they are just lines, imaginary lines. So these lines represent the path of an imaginary independent pole. If they upload you, they are imaginary lines. So definition of magnetic field lines. Now look, the path along which unit north pole moves in a magnetic field is called magnetic field. That part which they move is called the magnetic field. Any part at which they move is called the magnetic field. If you notice, see north and south, they are attracted. Are you following? See north and north, they are repelling. They don't want to come together. See south and south, they are repelling. So that's what I was actually talking to you about. So now magnetic line of force. Magnetic line of force or magnetic field lines, they are the same thing. They are helpful to show the direction and strength of a magnetic field. They are helpful to show like this one, all these lines now, they are called magnetic line of force. So it's the one that will tell us that okay, this thing is attracting, and okay, this one is not attracting. So these lines are called magnetic line of force. If you notice, they have direction. This one is telling us that it's going up, this one is telling us that it's going up. If you notice, all these things, they are called direction. They are showing us direction. Look at these ones too. They have every lines will always have, they usually have the direction actually. So they always show us the direction. So see the direction of this one. You notice that all these ones, they are coming like this. You notice that all these ones too, they are coming like this. You notice that all these ones, they are going like this, they are going like this. So those are the things that are called magnetic lines of force. And apart from that, the functions of magnetic line of force, they said they are helpful to show us the direction, which I've said. And another thing is that they help us to know the strength of a magnetic field. So if there are many, if the magnetic line of force, if there are many, you will know the strength of the field, because I've told you earlier that the strength of a field, you can know it actually. So if there are many like this, you will know that the strength of the field here is actually much. So the direction of a magnetic field or any particular space, or at any particular space, is the direction in which the north pole of a magnetic compass needle point if placed at that point. The strength of a magnetic field is shown by how much close these lines are to each other, so in their respective. So if, like, for you, if you want to know the strength, apart from them being many, the closer the lines are, you get, if the lines are extremely very close, that means the strength of that means that field has a very high intensity. That means if the magnetic field is very strong, it has a very high intensity. So that's that about that. So for us to know that, is to know the strength of a magnetic field, we know it by what, how many magnetic field lines we are having and how close they are. So lastly, okay, not lastly, we have the strong and weak magnetic field. The strong magnetic field, now let's say if magnetic fields are very close to each other, that is that magnetic line of force, if they are close to each other, then it is strong. But if they are not close, if the magnetic field lines are far away, if they are far away from each other, then it is a weak magnetic field. Are you getting it? So that one is as simple as that. Types of magnetic field. We have the uniform magnetic field. Magnetic field is said to be uniform if its magnitude is equal and direction is same as every point in the space. But when it is non-uniform, magnetic field is said to be non-uniform if its magnitude is not equal and direction is not the same at every point in space. So when they ask you about uniform magnetic field and non-uniform magnetic field, this is it. Okay, so if its magnitude is equal and the direction is the same at every point in the space, if the magnitude is the same at every point in the space and the direction is the same, then it is a uniform one. From the word uniform, whenever you're talking about anything uniform, you're talking about everybody is the same. That's why everybody will have, that's why you all have a uniform whenever you want to come to school, because uniform, anything called uniform in English language means they are all the same. So when something is non-uniform, that is the magnitude is not equal, that is the magnitude of the magnetic field is not equal and the direction is not what, equal at every point in space. And lastly, properties of magnetic field lines. Magnetic field lines are close continuous curves. Magnetic field lines emerge from a magnet at north pole and enter the magnet at south pole. Let us confirm this from the pictures we have. They said they emerge from the what? Let's check again. It says it emerged from the what? From the north pole and enters the magnet at the what? South pole. Let's see how the magnetic, let's see how true that is. If you notice, see the direction of these magnetic field lines. You see, it's like this, they are coming from the north and they are about to enter the what? The south. So that means it's true. Let's look at this one too. They are moving from the north and they are about to enter. So actually you must know that as one of the properties of a magnetic field line, that they tend to move from the north pole and enter into the south pole, and they are closed continuous curves. As you can see, they are all curvy lines actually. And that thing is that the tangent at any point on the magnetic field line give the direction of the magnetic field. So all those, I've told you that it helps us to show the direction of the magnetic field. So that's what that point is trying to say. And another thing is saying that no two magnetic field lines can intersect. They don't meet. They are lines that never meet. So you cannot see them crossing each other. You cannot see them crossing each other like this. Like, let's say, sorry. You cannot see them crossing each other like this. No. They won't cross each other like that. They are curvy lines, but they will never meet. They are lines that never meet. They are lines that never meet. They cannot meet. Intersect means they don't meet. They can't intersect. They can't cross each other. So that's another property. And the last property says magnetic field lines are crowded. That is close to each other in a region of. They are close to each other in a region of weak magnetic field. They are crowded. That is close to each other in a region of weak magnetic field. What do we say? We said in a weak magnetic field, they are far away from the magnetic field line, are far away from each other. Then the strength of the magnetic field in that region is very small. So I think that statement there is just trying to say forget about in a region of magnetic field. Actually, let's cancel this out. Actually, let's cancel this out. Let's cancel this out. Let's cancel it out. So just say magnetic field lines are crowded or close to each other. So like that, we have actually come to the end of the class. So I'll drop your assignment on the assignment portal. Make sure you please check the assignment portal. I am begging you. And if you have any question, please send your questions to the readable. You see a portion of the readable where you can ask questions, and in the next class I'll either answer it like this or I'll send you answers to the readable. And thank you for listening. If there are any questions, you can actually send them to the readable. God bless you. Bye.